Alright, we're going to get one more presentation in, and this is going to be an example of a survey of different topics inside of computer architecture. For those in computer science, there's going to be the HPC section, which stands for High Performance Computing, which talks about how to increase the performance of our machines through different pieces of software and different hardware techniques. For those of you in security, there is a security section in architecture as well, and I'll go through a couple of those. It really depends on the subject. How that goes through. So what's going to happen is, the last day of class will be a survey of different high-performance computing technologies and architecture-related security vulnerabilities. Today I'm going to present on MPI, OpenCL, and Rowhammer. These two are definitely high-performance computing technologies, and Rowhammer is a security vulnerability. The last day of class is April 28th. You'll present, that's not Monday, that should be a Tuesday. April 28th, 2020. I understand everyone's at home, so you will be uploading a YouTube video. Here's a couple of different topics. HPC, I've listed different ones right here. Nobad, Hadoop, Spark, etc., etc. Security, here's a bunch of them as well. There are plenty more out there. If you need more ideas or these are taken up, please email me and I will give you some more ideas, or if you can find something else that has at least somewhat something to do with architecture or operating systems, I will definitely allow that. So, a little more about the survey. I'm going to present three so that you'll have an idea of what I'm looking for. But make sure you answer these questions. What is it? How does it work? How does it help high performance computing? Or how does it break security, or what's the vulnerability? How does it relate or use to MPI Blast or OpenCL? For those of you in security, you can just go ahead and completely skip this one. Why is this software useful over or in conjunction with MPI Blast? And how popular is it and who uses it? For the security side, let me go ahead and rewrite that. What is it? What type of vulnerability? Is it a privileged execution or remote execution of code? How does it work? How does architecture play into this issue? Is there a way to patch the problem, or are there workarounds? And how concerned should we be about this issue? Some of them, here's for example Spectre, which I will get to probably next time, is basically a vulnerability that's just going to happen. There's not much we can do about it, but our concern is very low because it's incredibly hard to pull off, and two, every time you do a software update, it completely breaks Spectre, and then they have to go through this long road of trying to update it again. So the concern, or in the case of Meltdown, you should be very concerned because it's just a flat-out vulnerability that reads all your passwords. All right, one person per topic, so this is going to get very interesting because the size of this class is extreme. 10 to 15 minute presentations, April 28, 2020, not 2019. The topic selection is definitely first come, first serve, starting now. So go ahead and email me. You may take slides from the internet, just like I've done with MPI, OpenCL, and Rowhammer. Just be sure to cite them, and that should have been with a C and not an S. And I will show you all that starting now. Let's see, let's go ahead and close that. Let me go ahead and move over into my lectures. And let's see, we've got... Where is MPI? There we go, 17.0 using HPC with MPI. Great. And whoops, that's not what I meant to do. Of course, this is a giant nightmare because I can't just full screen anymore because that would make too much sense. Alright, hopefully that looks fine. So I'm going to talk about message passing interface. I totally took these slides from Mr. David J. Howard from, it looks like Minnesota State University? Sure. And I'm presenting them. There you go. See, that's all you got to do to cite it. Slides by and presented by you. Boom, we're done. Alright, so he went through in his discussion about an actual MPI that he set up on his university, so he's going to talk about that. It's a 35 node cluster, has one master and 34 workers. So this is definitely a master-slave relationship. Each worker has two dual-core AMD Opterons, so that's 4 actual units, 8 gigs of RAM and 80 gigabytes of disk space. Head node has 7.4 terabytes. This is very common in HPC for all of the workers or slave threads to have a very low amount of disk storage. disk storage, but the head node will have a significant amount in order to store the results. So the operating system, Red Hat, you can SSH over to it and share a Scala pack. We'll just keep going. Alright, so message passing model. A process traditionally is just a program, so it has a counter and address space. So what's going to happen is, with message passing, the idea is that one program is going to have a message that it's going to send to another. This is a little different than the shared memory model, where two processes are going to share a piece of memory and communicate there. In message passing, one node is going to basically wrap up a message, throw it over the fence, and then someone else is going to read it. And that's how MPI works. Now, this is an inter-process communication, so it's a process level. And the reason for this is MPI works on the network level, which means that it connects machines over a network, either an Ethernet or a high-performance plane, which would be something like InfiniBand. And MPI is used, or message passing is to move data from one processor space to another. So it's going to copy the data, it's not going to share the data. Wrong button. So it's going to look something like this. Process 0 wants to send the data, and process 1 will receive the data. So data is explicitly sent by one process to another. There's no implicit data transfer that would be in a shared memory model. Or put the data into process 1 memory, or the data in process 1 can also get the data from another process. But the point here is that these are explicit commands. The other version of this is if there was a memory that both processes shared and they could just read and write directly to it. But this instead is trying to move data, usually over Ethernet, from one process to another, or of course this is the other version. This arrow should actually go the other direction. A message passing library, yeah. So this MPI is actually a library, it's not a framework. So it's something that your program utilizes in order to facilitate communication amongst machines. Now you could write this all using sockets and whatnot, but that becomes very tedious and error prone. So what MPI does is it actually simplifies this whole process and gives you a standard model in order to do or facilitate this communication. Again, it's available in C, C++, and Fortran currently. It's mainly used for, end users, library writers, tool developers. Great. MPI is actually an older technology. I believe it was developed in the 80s, so it is pretty old, but it is still used a lot. And a lot of times nowadays, MPI is what's running under the hood amongst other type of libraries in order to facilitate this communication. And the reason for that is there's been a lot of work on MPI in order to make it simpler and in order to improve performance of MPI. So a common example of a program in C, notice you have an MPI.h file. You still have standard I/O in the standard domain like normal, but the big trick is before you use MPI, you do have to call init in order for MPI to initialize, and then before you exit, you want to call finalize. The reason for this is init will go ahead and take your process and set up the connection with the master thread, and then finalize is a way to tell the master thread that, hey, look, I'm done doing my work, so you can deallocate me from the space of processes that can work on data. It's important that you do these two. Here's the Fortran version for all of us Fortran lovers. So yeah, notes on C and Fortran, they're actually calling basically the same thing as well as C++. And that's really all that matters in this slide. So by default, all errors will cause MPI to straight up abort, but you can set up exception handlers if you want to, and libraries are very common or commonly set up these exceptions for you. So most people that end up using MPI are using a library on top of MPI. Alright, in order to compile it, they did modify a compiler. Usually it's a wrapper around GCC. So you have to call MPI-CC, which is the MPI compiler. Naturally, there is the C++ version and then the Fortran version as well. The reason for this is it needs to set up the binary so that it knows how to actually communicate with master thread. To run it, you want to call MPI exec in front of the program itself. Alright, so here's some quick examples. MPI exec, and this is where you send the number of processes you want, and then the binary itself. This would have 4 processes, this would have 2 processes. And the idea is after you executable, anything you want to pass to it would come afterwards. Okay, so I talked a little bit about how you compile and set it up. 2 important questions: how many processes are participating and which one am I? So when you write your program, you need to figure out how many processes there are in total and which one you are. And this is very common if you want to split up the work. For example, if you're doing a parallel merge sort, you need to know how many processes there are so you know how big the piece of data or the sorting piece of data you need. And then you need to know which one you are so you know which piece of the data you're operating on. Com size tells you the number of processes, and the rank is the process number you are inside the comp size. So, a better version of C, notice we still have init and we still have finalize, and it's very common for the rank, MPI world, get your rank, get your size, and so you can say I am process whatever of whatever, and there's your rank and the number of processes. This first element, MPI world, you can set up groups in order to, and you can have like different subgroups working on different pieces of a problem. MPI world just says go ahead and give me the entire world or how many processes there are. And there's the C++ version and of course the Fortran version. The nice thing about MPI and the reason why it became so popular is it's very simple to use. If you use just these 6 functions, you can actually do any type of processing. As you'll find out, these 6 are limited in some performance aspects, but the reason why people like it is with these 6 functions you have basically everything you want. Init and finalize to set it up, comp size and rank to know which process and how many processes there are, and then send in order to send data to a process, and receive in order to receive it from another way. And if you think about it, in order to do anything or accomplish any work, those are the 6 that you're going to need with MPI. They may not be the most high performance, but with those 6 you can get anything done. Now, they did find out while developing there were a couple of things that would have been very helpful in order to facilitate communication. So there's different types of other operations. You can synchronize with barrier. You can move data with a lot of different calls, basically broadcast, that's bcast, scatter, gather, and all to all. And then there's other ways to do a group communication. And these functions were used because they found out that there was a lot of work that people were repeating with send and receive. And if MPI took care of it underneath the hood, then it would actually be more high performant and it would help ease some coding because people keep using these all the time. Let's keep moving past this. Here we go, barrier. So barrier is a simple one. What you do is you call barrier in MPI world, and what it does is make sure that all the processes that we're working on, let's say any piece of code over here, they're all going to wait to the barrier. Once everyone gets to this barrier, which is this piece of code right here, it then lets them through. The reason this is important is a lot of times what's working over here may require another process to finish back here. So barrier just makes sure that everyone has completed their work so far up to where each one calls barrier, and then they're allowed to continue from there. It does affect performance, and the reason for that is that if you have basically all your processes here except one who's really dragging, all these processes that could be doing useful work are waiting on this process back here. So it is recommended you don't use this, but the nice thing about barrier is it does simplify a lot of work. Now, broadcast ended up being a very popular or very useful function. The idea is you may have one process as a piece of data and you want to copy it to everyone else. Normally the way people do it is they send one here, then one here, then one here, then one here. But MPI found out a better way to go about this because this is an O of n algorithm. It's copying one by one up to n processes, or n minus 1. And O of n is actually slow, especially when you can come up with another method, and they don't give a picture of that. But the idea is once this guy sends here, he can also send while this one can also send. So at first only one guy can send, then 2 guys can send. And since these 2 guys are sending to others, that means you can have up to 4 guys. And then since you have 4, you can go up to 8, and then 16, then 32, then 64, etc., etc. If you look at that, it's going to grow exponentially, which means that calling broadcast is now a log of n algorithm instead of an O of n algorithm, which is significantly faster. Gather is the same thing as broadcast, just in reverse. So let's say everyone has one piece of data. This is very common inside of sorting because these are the different arrays that each one's sorted, and they want to be copied back to a master thread. So the master thread might gather them. Again, you can do something similar like last time, since B can send to A, D can send to C, and E can send to the master thread, and then these two can send their different chunks. The reason why that can be faster, although not always, is because inside of Ethernet, if you recall, sending a packet, a 1-byte packet, or I believe a 64 kilobyte packet, is the same, or I shouldn't say the same cost, but has a very similar cost because most of a lot of cost in Ethernet is the overhead of sending a packet. They do a gather example, but I don't think this is necessary for this presentation because we've got pictures. Gather to all is another common one. Everyone has a piece of data and we need to copy it to each one. Again, you can do something similar with the log of n, but the idea is you copy each one to every other piece of information. And then scatter. This one is very common, for example, if you're sorting, because each one needs to work on their one piece, so you scatter all the data to each one. Again, you can sometimes do a log of n, although not always with this one. We don't need an example. All to all, this one's a little more confusing. I'll go over it real quick, but it doesn't make much sense until you're doing a very high performance situation. There are very few examples where this is used, but it was used enough to make a library. Notice that this A0 through A3 then becomes the first element of each guy. B here becomes a second. P2 here, and then P3. This is just a way to split up. It's very good for matrix transposition. It ends up being for fast Fourier transforms as well, but y'all probably have not encountered that yet. That's a good example, but we don't need to go through it. The last one we want to talk about with MPI is called reduce. And what this does is it takes all the pieces of information on the different processes and reduces them into some final value. For example, you may want to sum every value, and so you could call reduce, telling that it's going to reduce it inside of addition. For example, logical AND, logical OR, bitwise AND, and you might have get the max as well. All reduce is something similar, but it also sends it to each piece of process. Notice that most of these things have an all version, and the all version sends the answer to everyone, as opposed to just one. All right, we're skipping scan because that's not important, and I think that's actually going to be it for MPI because we don't need anything more. So this is the point of MPI. A couple things I did not cover. I talked about why it is, how useful it is. It's used a lot. Why is this related to architecture? Because this works on the process level. And that is a more of an operating system thing, but it does work over Ethernet in order to take advantage, or I should say InfiniBand is usually what people use nowadays as well. And it ends up being very popular, although very few people actually use it directly because most of the time it's used underneath the hood, or namely inside of other libraries. All right, and that's it for MPI. I will talk about OpenCL next.